This is Mr. Anderson from Kellogg Community College. We're going to be talking today about intersections, unions, and compound inequalities in Math 121, Intermediate Algebra, Chapter 4, Section 2. We are familiar with set builder notation, and we're familiar with set builder notation from when we talked about domain and range. For example, we've had some situations where the domain was where the x was between maybe -5 and +10, including the -5 but not including the +10. This is just an example of what we've seen. But we're going to deal with some finite sets. For example here, I'll make a finite set of some numbers, let's say 1 through 5 whole numbers. And that's an example of a finite set. And I can also make another finite set if I want to. This is going to be the finite set B of, let's say, maybe 2, 4, and 6. So even numbers 2 through 6. The union is represented with a kind of a large U, and the union is basically between like two letters would be all the elements of both sets. The intersection would be only what the two sets have in common. So if you take a look at A and B, the union would be 1, 2, 3, 4, 5, 6 because it includes all the numbers of both places. The intersection, which is that only what they have in common, would be 2, 4 because 2 and 4 are the only two things they have in common. So the union is going to be every element of all sets. So I'm just going to write down every element. And the intersection is going to be only what they have in common. So have in common. Now let's take a look at a Venn diagram. If I was to draw a Venn diagram, this Venn diagram of the word union would be everything in both sets. So if this was set A and this was set B, we would write 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, because this circle on the left is 1, 2, 3, 4, and 5, and the circle on the right is 2, 4, and 6. You'll notice that this on the inside right there is the intersection, so 2 and 4 belong in both circles, like in a MasterCard logo. Now, the Venn diagram of the intersection would just include the 2 and the 4, because this is really the only thing they have in common. So the Venn diagram of the intersection is just this inner piece, and the Venn diagram of both elements A and B would be every single thing that they have in common. So the word or means I want A or B, which can include anything from A or B, and is including I want the numbers in A and B, which is exclusive to these two. So the answer for A union B is going to be 1, 2, 3, 4, 5, and 6. The answer for A and B is going to be 2 and 4. Okay, so what we have is that. Let's do some examples. All right, a couple of examples right there. The union of A and B is going to be every single number in these sets here. So 1, 2, 3, 4, 5, 6, and the number 8. So it includes every single number from A, and there's serious overlap between A and B, because B is 2, 4, 6, and 8, so there's that. Now the intersection is not going to be as big, and it never should be. The intersection of these two sets is whatever they have in common. So they both have a 2, they both have a 4, and they both have a 6. So this is 2, 4, and 6, that finite set. Now here you see that the A union B is 1, 3, 5, and 2, 4, 6, and 8. So to put this in order, the union is going to be 1, 2, 3, 4, 5, 6, and 8. But the intersection of these, you'll notice that there is no overlap. So it's an empty set. There is no overlap between these two sets. Now, x is even and x is odd. The union of these two sets is going to be all evens and odds. And if you look at all evens and odds throughout the universe, x is going to be, you could write down all even and odd, but technically these are the integers. integers are positive, negative whole numbers. For those of you who thought, like, well, what if they're well, couldn't they be just this be real? But, well, that would include fractions and decimals, and we don't know even and odd fractions and decimals. So, integers. Now, what do they have in common? Well, nothing. The odds and evens are separate sets, so there's the problem. Now, what if x is real and the empty set is the extra set? The union of nothing and all real numbers is going to be, well, x is going to be real. And what is the intersection? What do these have in common? Well, if you have the real numbers and you have the empty set is their only thing in common. All right, let's go to the next problem. Since that's way near, I think I can fit it in. Yeah, I'm not quite at the bottom of the screen here. X is greater than 5, x is less than 5. Well, on a number line, you would see that would be everything bigger or smaller than 5. So x would be where x cannot be equal to 5, because you have every single number in the universe that is real except x can't be 5. Now, the intersection of this, what do they have in common? There's no overlap between these two either, because one line goes in one direction, and I'll show that to you on a number line here. One line goes in one direction like this, and one line goes in the other direction like this. There's technically no, even though you may not see this little space right there, there's technically no overlap. So the union of these two sets would be everything but 5. The intersection is nothing. So let's keep going from here. All right, we're going to graph and write some interval notation for these compound inequalities. This is your next homework piece here. So let's see here. -5 is less than x, which is less than or equal to 0. So on my number line, I'm going to probably put down a -5 and a 0. Now it looks like I'm not going to be able to get to -5, so this is going to be a curved line like that. And it looks like I'm going to be able to get to 0, so this is going to be a hard bracket like that. And I'm going to draw the line between the two of them, because x is between -5 and 0. And so my notation can be written one of two ways. My notation is going to be written with soft parenthesis, -5, comma 0 with a hard bracket. Also the set builder notation x, and we have -5, which is less than x, which is less than or equal to 0. So if you compare the original problem to the set builder notation, you can see that it's pretty much the same thing. Just it's good to have on graph just so we can see what's happening here. All right, I need to make a quick edit here, so you'll see the top part just went away. Sorry about that. So here I have x is less than or equal to 3, or x is greater than 2. Now this is the union, and it's the union so we can use both equations. Let's write this in here. This hard bracket is going to be at -3, and it's going to go less than or equal to. This is going to be a soft bracket going to the right, and that's going to be x is greater than 2. This is going to go to -infinity. This is going to go to positive infinity. So my notation, our set builder notation, will be x, and x is going to be either less than or equal to -3, or x is greater than 2. Now you can see that again, that's very similar to this. But if we were to write now my other notation, which is going to be writing things with parentheses and hard brackets, this would look like soft parentheses, -infinity to -3 with a hard bracket here. And we want union because that's or. And then we're going to have the other one right here, which is going to be a soft bracket because it doesn't quite match the 2, doesn't quite reach the 2, and that goes to positive infinity. Positive and negative infinities always have the soft brackets because we never quite get there. Now, this is like the problem above it, and it's probably good to point out that this is going to be an intersection, and it's an intersection because it's between two numbers. This is -6 and this is 3. Also, this is going to be hard brackets because we can actually reach -6 and 3. So let's put a solid line between the two of these here. Okay, so set builder notation is pretty easy because you're just going to rewrite your problem that you have. Now we're going to have between negative 6 and 3, and take a look at this. It's going to be negative 6 comma negative 3. Since the and is going to be between two numbers, we're never going to have a situation where we're going to have these separate parentheses with the interval notation there. This is always, union will have to be split up, but the intersection will always be, inclusive like that. Okay, let's try this one. This is another union problem, and it's a union because it's or. I can either have x less than 0, so here's my 0, and it's going into the negatives. It's going into the negatives to negative infinity. And this is going to be the 1, so it's going to be positive. So this is going to go to positive infinity. Okay, so my set builder notation is going to be what was written in the problem. X is less than 0, or x is greater than 1. Sorry about the bad penmanship. And in this case, we're going to go from negative infinity to 0. And the union, notice soft parenthesis because it never quite got there, parenthesis 1 to positive infinity. All right, let's keep going and see some more examples here. All right, we've got some interesting ones to talk about right here. This one here, x is greater than 3 or x is 5. Whoops, forgot to change to a pen. So that little box is going to be part of my union. And it's union because it's or. And so therefore we're going to have x is greater than 3. So here's 3. And we're going to have a hard bracket going to the right. Now watch what happens here. I have x is greater than 5. Now notice that this is still part of it. Now if I want both, I basically take all the numbers from here to the right and then all the numbers from here to the right. So my answer is going to be simplified to this. X is greater than or equal to 3 because it included all the values right of that 3. So we don't like writing this is redundant. So my answer is going to be hard bracket negative 3 comma parentheses for the infinity. So you'll notice that all of these are going to be kind of special, especially with the words here, because you'll notice this is the same problem, but it says and. So it's the same picture as above. See, I have negative 3 going to infinity, and I have, positive 3 going to infinity, and I have 5 going to infinity, but since it's and, I'm only looking at what they both have in common, and that will be this bracket right here. This bracket starting at 5 is the only one that's going to be counted because it's and. I want this condition to be satisfied. I want this condition to be satisfied. And 3 is not in both sets. 4 is not in both sets. So my answer is going to be x is greater than or equal to 5. Or 5, which is to infinity. Wow, why did I just missed that negative there? So sorry about that. Let me fix that. I know that was probably bugging some of you while watching this. Thanks for sticking with it. All right, so now I'm looking at x is less than 5. All right, so here I have a bracket here. X is less than 5, so I'm going to draw this all the way down there. And x is greater than 2. Watch this. I'm going to go greater than 2. Whoops, I'm going to have a little curvy symbol there. But since this is a union, which means I have everything from both sets. I got one set going this way, and I got one set going this way. That means that every single number is covered, so x is real. Or I'm going from negative infinity to positive infinity. Now check this out. I want x to be less than 3, so let me put a positive 3 here in a square bracket that goes in this direction here. And I want x to be bigger than 5, so 5's over here. Okay, so 5. But notice it says and. So what numbers are both less than or equal to 3 and greater than or equal to 5? Not a darn thing. There is no overlap with the and, so the union of the 3 numbers less than 3 and numbers or less than or equal to 3 and numbers greater than or equal to 5 is nothing. All right, let's go do some more problems. All right, we're going to solve and graph in interval notation. Now, to solve and graph, what you have to do is the problem twice. You got to do the problem twice. So the first thing you're going to do is do the problem here, which is going to be negative 1 is less than or equal to x minus 3. And then we just solve for x. Add 3 to both sides. This makes positive. Whoa, wait, hold on a second. Add 3 to both sides. That makes a positive 2, which is less than x. And I'm going to flip this around using the symmetric property. X is greater than 2. Now we're going to do this problem here. So x minus 3 is less than or equal to 5. It should be a 3. So I move the 3 to the other side. X is less than 8. So it looks like x is greater than 2. X is less than 8. So here's 2. Here's 8. That is a less than or equal to sign, so this is going to have a square bracket here. And this is going to have a curve right here. So it's going to be between these two numbers, like so. And I'll show you the right notation. The set builder notation is going to be x, and it's going to be from negative 2 to 8. There's our set builder notation. And interval notation is going to be soft parenthesis on the 2, hard bracket on the 8. Again, we're going to do the problem twice here. We're going to do this like so. So this is going to be negative 18 is, that should look like an 18, is less than 4x plus 2. Subtract the 2, so negative 20 is less than 4x. Divide by both sides by 4, you get negative 5 is less than x. Now we're going to flip that around. X is greater than negative 5. And try this one on for size. 4x plus 2 is, 20. Ha! Where'd that come from? 4x plus 2 is less than or equal to 30. I'm going to move the 2 to the other side. 4x is less than or equal to 28. And divide both sides by 4. X is less than or equal to 7. So let's see. X is greater than negative 5. So this is going to be a soft parenthesis at negative 5. And x is less than or equal to 7. We're going to put a hard bracket at 7 and connect the dots between the two of them. All right. Looking good. So let's look at our set builder notation. We have negative 5, which is less than x, which is less than or equal to 7. And if we're looking at our interval notation, negative 5 comma 7 hard bracket, having to deal with what the symbols are over here. Now here are two problems. We've got one on the left, one on the right. They're both and equations, so this is going to be the intersection. So after we do the problem, we're going to graph it and see what these two things have in common. So our first problem over here, I'm going to solve for it by moving the 5 to the other side. Negative 9 is less than 3x. We're going to divide both sides by 3, so negative 3 is less than x. Rewrite it, x is greater than negative 3. Do the same thing over here, add 7 to both sides, so we have 2x is less than or equal to 10 in this case, sorry. Divide both sides by 2, x is less than or equal to 5. So here I have a situation where x is greater than a negative 3, so I'm going to put a curve right there for negative 3, and that brings it forward. And this is going to go all the way to a positive infinity, but I notice I have another place around here. This is going to be 5. This is going to be a hard parenthesis, and this is also going to go to negative infinity, but since I'm looking at the word and I want to see what they both have in common, we're going to then look at this as their answer. X is going to be between negative 3 and 5. Be careful though when you do that you put the right symbols for less than in the middle of the problem. And then we will go and use our interval notation, soft parenthesis negative 3, hard parenthesis at 5. There we go. Okay, what we're going to do is we're going to do this problem twice. We're going to do this side first, and then do this side next. So I'm going to have negative 10 is less than x plus 6 divided by negative 3. To get rid of the 3 from the denominator, we multiply both sides by negative 3. Negative 3's get simplified, so I get 30, which is greater than, notice the symbol flips, x plus 6. Then I move that to the other side, so 24 is greater than x. Because I want to read this a little bit better, I'm going to move the x to the other side. X is less than 24. So I'm just using the symmetric property to go from here to here. Now let me talk about this. The other part, x plus 6, which is over negative 3, is less than or equal to negative 8. Multiply both sides by negative 3. Negative 3 simplify. X plus 6 is equal to 24, but wait, the symbol does flip again because we multiplied by a negative. Moving the 6 to the other side, x is greater than positive. 18. So I've got x is less than 24 and greater than 18. So it looks like I'm going to be between 18, this is a soft parenthesis here, x is greater than 18, but less than 24. So my set builder notation is going to be 18, 24, like so. And my parentheses is going to be 18, comma 24, like that. That's my interval notation. All right, let's see what we got here. I'm going to move, this is and, so let's see where our intersection gets us here. I'm going to move the 5 to the other side, so this is negative 9. This should look somewhat familiar. Is less than or equal to 3x, or less than 3x, and we multiply or divide both sides by 3. X is greater than negative 3, and I'm going to flip that around so it's a little easier for me to read. X is greater than negative 3. I'm going to move that to the other side here. This is 2x. This is going to be less than or equal to 10, since I moved the 3 to the other side. Divide both sides by 2. I get x, which is less than or equal to 5. So if this is the case where it's the word and, as it was in the previous problem, we are going to basically get these two and see where they end up on the graph. So with that in mind, I'm going to have a number that's greater than negative 3, soft parenthesis, but I want x, which is less than 5, hard bracket. So here's my setup, just like it was before. I've got between negative 3 and 5, but look at where my less than or equal to signs and my less than signs have to be in a certain position. Now, I think what's kind of interesting is you'll notice that this is x is greater than negative 3. Take a look at that. It's still read x is greater than negative 3 if I read in that backwards direction. My interval notation is negative 3 comma 5 hard bracket. Finally, what does this problem have to do? Well, this is going to be substituted in for my f of x because that's my equation. So I'm going to have two equations to solve. 2, which is less than negative 3x minus 8, and I'm going to have another equation which is negative 3x minus 8 is less than 4. So let's show this workout here. I'm going to then get my 8 to the other side, so by doing that I get 10, which is less than negative 3x. I'm going to divide both sides by negative 3, so I'm going to have negative 3 1/3, or negative 10/3, is going to be greater than, notice the symbol flip, x, because you flip the symbol because you divide it by a negative. Now I'm going to flip the symbol again because I'm going to use my my symmetric property to get me that. So x is going to be smaller than 3.5. Now let's see what this is going to be. I'm going to add 8 to both sides. So I got negative 3x is less than 12. Divide both sides by negative 3. This flips the symbol. X is going to be greater than negative 4. So I am looking when x is going to be less than 3.5 and greater than negative 4. This is important to know that on a number line, negative 3 is here and negative 4 is here. So you want x less than 3.5 but greater than negative 4. You're looking at just this space between negative 4 and negative 3.5. So this is an AND problem. Since we want both criteria to be used, if it's between the two numbers, it's always an implied AND or intersection problem. And we're going to have negative 3.5, which is less than x, which is less than, oh, Snapple, hold on. I put that number in the wrong spot. This should be negative 4, and this should be negative 3.5. Sorry about that. Just had those reversed. And it's barely on the screen. And then my interval notation is going to be negative 4, comma, negative 3.5. soft parentheses because these were not less than or equal to symbols. Well, thanks for watching.